Imagine a phone cord,
Yeah.
right? And it's just been completely snipped.
Yeah, clean break.
Exactly.
Wow.
On one end, you've got a fully functional supercomputer. That's your brain. And on the other end, there's this perfectly healthy piece of hardware like your leg muscle.
Right.
But the signal is just dead.
Mhm.
I mean, the muscle is sitting there, totally viable, completely primed for action. But the command center, it just cannot get the message through.
It's completely isolated.
Yeah. And for over 80% of stroke survivors, this isn't some abstract analogy. It is a daily, very physical reality that they wake up to.
It really is. And that severed connection, it represents just a profound loss of independence. Because after a neurological event damages the central nervous system, we see this massive disruption in synaptic transmission.
The signal just drops.
Exactly. The motor neurons that traditionally, innervate those muscle fibers, they simply go offline. The software can no longer drive the hardware.
And today's mission for this deep dive is looking at exactly how we bridge that gap. We are exploring how a surprisingly old technology, basically zapping muscles with electricity, is currently being deployed to, quite literally, rewire the brains and rebuild the muscles of older stroke survivors.
It's incredible stuff.
It really is. And to do this, we're pulling from a really compelling stack of sources for you today. We've got a rigorous, peer-reviewed medical review published in the Annals of Geriatric Medicine and Research.
Yeah, authored by a clinical research team at Kyung Hee University in South Korea.
Right. Alongside a companion blog post that kind of translates these findings into everyday practical takeaways for patients. Okay, let's unpack this, because the raw physical toll of a stroke is immense, and the numbers from this review, they set a very sobering baseline.
The baseline is, it's critical to understanding why this research actually matters. Stroke remains the third leading cause of death worldwide.
Wow, third.
Yeah. And the mortality rate claims roughly 1/3 of patients, while another third will, unfortunately, experience recurrent secondary strokes.
That's devastating.
It is, but our focus today is really that remaining third, these survivors who are left navigating severe, life-altering mobility limitations.
And the statistic that really anchors this entire discussion is that more than 80% of those survivors have gait impairment. Like, they cannot walk independently to perform normal daily activities.
Right, which takes a massive toll on quality of life.
Absolutely. And the tragedy of that disrupted synaptic transmission is that the tissue doesn't just, sit there dormantly waiting. Denervation triggers this massive inflammatory cascade, and we see 𝘀𝗶𝗃 set in with terrifying speed.
Terrifying is the right word, because the muscle tissue, it actively remodels itself in the absence of that neural signal. Because of that sudden disuse, you see a really rapid decrease in the number of active motor units.
So it's essentially breaking itself down.
Yeah, the structural degradation of the tissue happens incredibly fast. And this completely upends the old school mentality that resting is the best rehabilitation strategy.
Right, because if you just rest...
It gets worse. Active intervention is really the only way to stop that architectural collapse of the muscle.
Which brings us to the technology itself. Functional electrical stimulation, or FES. Some listeners might know it as EMS technology, from those late-night infomercials.
Right, exactly.
But diving into the Kyung Hee University review, we realize this is not some contemporary Silicon Valley biohack. The foundational roots of hacking the nervous system with electricity, they go way, way back to the 1700s.
Yeah, Luigi Galvani's work in the late 18th century, that really laid the groundwork for everything we are discussing today.
The frog guy, right?
The frog guy. Galvani was the first to rigorously experiment with applying electricity to the leg muscles of frogs. He proved that an electrical current actually induces localized muscle contraction.
Which is wild to think about happening in the 1700s.
It was revolutionary. It was the first real proof that biological tissue responds mechanically to an exogenous or outside electrical stimulus.
Right, like the classic high school biology frog experiment. But the leap from observing a frog leg twitch to actually applying this to human stroke rehabilitation, that took a surprisingly long time. I mean, we didn't see the next major milestone until the 1800s.
Yeah, that was Duchenne, the French neurologist.
Like Duchenne muscular dystrophy.
Exactly, same guy. He pushed the field forward by developing a non-invasive methodology. So instead of exposing the nerve directly, Duchenne figured out how to stimulate specific muscles using electrodes just applied to the surface of the skin.
So no surgery required.
Right. He essentially mapped the muscular system of living patients just by figuring out exactly where to apply current to trigger individual muscles.
But even with Duchenne's surface electrodes, they were mostly using it as a diagnostic tool. right? Or just for static therapy.
Correct.
Because the modern breakthrough where FES becomes a dynamic functional rehabilitation tool, that didn't happen until 1961. That's when 𝘀𝗻𝗃 introduced the idea of using electrical stimulation specifically to correct human gait disorders in real time.
What's fascinating here is the conceptual shift 𝘀𝗻𝗃 introduced. He realized that a continuous, steady electrical current just isn't helpful for a dynamic activity like walking.
Right, because walking isn't just tensing your muscles and holding them.
Exactly. You only need the muscle to fire during a very specific fraction of the gait cycle. By timing the electrical stimulation to basically mimic the natural firing pattern of a healthy nervous system, 𝘀𝗻𝗃 transformed a static laboratory curiosity into a functional mobility tool.
It's like the telephone line between the brain and the leg has been cut, and the muscle just wastes away waiting for a call. And 𝘀𝗻𝗃 figured out how to fake the call at the exact right second.
That is a perfect way to look at it.
So for over 60 years, we've had this basic blueprint. If the brain can't send the electrical signal down the spine to the leg, we can bypass the broken cord and supply the electricity from the outside.
Precisely.
But the mechanics of how we deliver that current today, they vary wildly depending on the severity of the case. So let's look at the hardware. The review breaks it down into invasive and non-invasive applications.
Yeah, so invasive FES involves actually surgically implanting electrodes directly into the tissue.
Ouch.
Yeah, or utilizing percutaneous electrodes that partially penetrate the skin to sit in really close proximity to the target nerve.
That sounds intense.
It is. Because this is an implanted surgical solution, it is typically used for long-term permanent management. We see it very frequently in spinal cord injury patients. And the electrical intensity in these implanted systems is generally fixed at around 25 milliamps.
Well, fixed 25 milliamps makes sense if it's surgically implanted. You really don't want to be constantly tweaking a system that requires an operation just to adjust.
Exactly. You want it stable.
But for stroke rehabilitation, particularly in older adults, where early intervention is key to stopping that 𝘀𝗻𝗃 we talk about, the non-invasive route seems far more practical, right?
Oh, without a doubt. The non-invasive method utilizes surface electrodes that just self-adhere to the skin, very much in the lineage of Duchenne's early work.
Just stick them on and go.
Basically, yeah. The primary clinical advantage is immediate accessibility. You can begin intervention incredibly early in the recovery process, which is crucial.
Because you aren't waiting for surgical clearance.
Right. Furthermore, the clinician has really granular control over the current amplitude. They can adjust it anywhere from 2 to 120 milliamps, depending on the patient's specific tissue response and tolerance.
That's a huge range.
It is. But both modalities, invasive and non-invasive, they have been clinically proven to effectively increase the cross-sectional area of the targeted muscles.
Okay, so the peripheral mechanism is pretty straightforward.
Right.
You place the pads, you turn up the amplitude, and the electrical current artificially forces the paralyzed muscle to contract.
Right.
It essentially serves as a mechanical workout, improving local strength, maintaining flexibility, and really driving blood flow into the tissue to prevent atrophy.
That's the peripheral side, yes.
But a localized peripheral workout does not explain the long-term clinical outcomes. I mean, if FES was solely a peripheral mechanism, the patient would instantly revert to paralysis the moment you peel the electrodes off.
Right, because the brain is still disconnected.
Exactly.
And that's where things get really amazing. The peripheral workout is really just keeping the engine running. The true rehabilitative power lies in what the review details as the central mechanism.
Okay, tell me about the central mechanism.
Well, FES does not solely blast an efferent signal like a downward command into the muscle fibers. It simultaneously stimulates the afferent sensory nerve fibers.
And because FES targets both the efferent motor pathways and the afferent sensory fibers, it's firing a massive feedback loop back up the spinal cord.
Exactly. It's not just a one-way street where the machine dictates the movement and that's it. The sensory fibers are actively screaming back to the central nervous system, confirming that the mechanical action actually happened.
Wait, so the electricity isn't just a physical workout for a dead muscle. It's actually a two-way street. It's like, we are hacking the nervous system to send an "I am still here" signal back up to the brain's computer to rewrite the software.
Yes, that is exactly what is happening. By forcing this continuous, prolonged peripheral stimulation, you induce widespread excitability within the human motor cortex itself.
The brain wakes up.
Right. The brain begins reorganizing the motor networks that are associated with those specific firing muscles. It is actively driving brain plasticity through that sensory feedback.
We're basically tricking the brain into healing itself. And the review goes even deeper into how that plasticity is achieved, specifically highlighting antidromic impulses.
Yeah, antidromic impulses are key here.
So if orthodromic is the normal pathway, like brain to spine to muscle antidromic means the electrical pulse from the ЭPS device is actually firing backward up the motor nerve.
Right, going against the normal flow of traffic.
Yeah, it's like a two-factor authentication protocol for the nervous system. The brain tries to send a ping down voluntarily, the FES sends a ping backward up the nerve, and when they meet at the anterior horn cell in the spinal cord, the system essentially verifies the connection and permanently saves the new pathway.
I love that. That two-factor authentication analogy perfectly captures the biological mechanism. When that artificial backward-traveling antidromic signal aligns with the patient's own voluntary cortical effort to move the limb, that is what promotes intense synaptic remodeling.
The intent has to be there.
Exactly. That pre- and post-synaptic coupling is the absolute prerequisite for lasting neural plasticity. The patient cannot just be a passive recipient sitting on a couch. Their active intent to move, combined with the electrical bridge we provide, that literally repairs the broken connections.
That is just beautiful. It perfectly explains the neuroscience. But, translating that cortical plasticity into a patient physically walking across a living room, that requires a masterclass in biomechanics.
Biomechanics are notoriously tricky.
Right. Because walking is essentially just a highly coordinated series of controlled falls.
Yeah.
And after a stroke, the timing of those falls is just completely shattered.
It really is. And the most visible manifestation of that shattered coordination in stroke survivors is foot drop.
Right, foot drop.
Yeah, it's a weakness in the dorsiflexor muscles, primarily the tibialis anterior, which is located along the front of the shin. And this means the patient cannot achieve adequate ankle dorsiflexion.
So they can't lift their toes.
Right. During the swing phase of the gait cycle, so when the leg is traveling forward through the air, the tibialis anterior fails to fire, the toes don't lift, and the foot just catches on the ground.
Which is an enormous fall risk.
Massive.
Yeah.
But the researchers point out something really important here. Simply slapping an electrode onto the shin to forcefully pull the foot up, that doesn't actually normalize the gait.
Wait, it doesn't. I would think that solves the problem.
Well, isolating the tibialis anterior definitely solves the immediate foot clearance issue, sure. It mitigates the tripping hazard. But the South Korean review highlights that targeting the distal extremity, the lower leg in isolation, fails to correct an asymmetric gait.
Ah, I see.
Yeah. The patient may clear their foot, but they are still heavily limping and shifting their center of mass super unevenly.
Because the failure isn't just in the ankle. The entire kinetic chain has been compromised by the stroke.
Exactly.
The asymmetry is often driven by a massive failure much higher up the chain, specifically the lack of activation in the hip abductors, like the gluteus medius.
Right. The gluteus medius serves as the primary pelvic stabilizer during the stance phase of walking.
The stance phase being that critical moment when the entire weight of your body is supported by a single leg.
Yes, and if the gluteus medius is weakened by the stroke, the pelvis drops dramatically on the unsupported side. This completely destroys the body's dynamic balance, and it just forces this heavy asymmetric limp.
Here's where it gets really interesting. The FES systems detailed in the review act like a real-time artificial central nervous system.
Yeah, they do.
They don't just supply a steady, dumb current. They utilize EMG-triggered stimulation. So electromyography actually reads the faint residual electrical signals that the muscle is still attempting to produce on its own.
It listens for the intent.
Yeah. So the system waits for the exact microsecond. The patient tries to shift their weight onto the leg for the stance phase, and then it fires the gluteus medius to lock the pelvis in place. And then, a fraction of a second later, as the weight transfers and the leg enters the swing phase, it fires the tibialis anterior to lift the foot.
It's basically a master puppeteer.
Exactly.
Yeah.
Zap the hip to hold the body up, zap the ankle to swing the foot forward.
And the clinical efficacy of this multi-channel EMG-triggered approach is profound. By normalizing both the stance phase and the swing phase simultaneously, we see chronic stroke patients achieve a highly symmetrical, highly functional gait.
Which is life-changing.
It is. And this biomechanical harmony translates directly to the hard data. The studies reviewed demonstrate significant increases in gait velocity during the 10-meter walk test.
Okay.
And that's alongside markedly improved cardiovascular endurance and overall distance on the 6-minute walk test.
So we see this beautiful orchestration of the gait. But temporary electrical timing doesn't entirely explain how the leg gets physically stronger over weeks of therapy. Like, to understand the actual reversal of sarcopenia we discussed earlier, we have to look past the nerves and into the actual muscle fibers themselves.
Too. We have to look at the cellular level.
And the South Korean review provides a comparative study here that is just staggering. They tracked post-stroke patients split into two groups. Group 1 received conventional rehabilitation, and Group 2 received conventional rehab paired with FES.
The divergence in their recovery metrics is really where the true potential of FES becomes undeniable.
Yeah, hit me with the numbers.
So the control group, relying strictly on standard voluntary rehabilitation exercises, they saw a 27.7% increase in ankle dorsiflexor strength.
Which, honestly, is a respectable, clinically significant improvement.
It is. You would be happy with that in a standard setting. However, the experimental group utilizing FES alongside their rehab saw an extraordinary 56.6% increase in strength.
Wow. A 56.6% gain versus a 27.7% gain.
Yeah.
The electrical stimulation is literally doubling the physical strength outcomes compared to voluntary exercise alone.
Because traditional rehab relies solely on descending voluntary pathways that are, already damaged. It just cannot adequately recruit the muscle tissue.
But FES bypasses the damage to recruit the peripheral system maximally, while simultaneously hacking the central system, like we talked about.
Exactly. And that massive disparity in strength gains forces us to look closer. FES is not merely a mechanical lever. It fundamentally alters muscle-specific transcriptional mechanisms.
Okay, getting into the biology here.
Yeah. When the electrical current induces a contraction, the muscle fibers actually synthesize and release myokines.
And because this is actively contracting the muscle, we aren't just seeing mechanical movement. We're seeing the release of myokines, meaning the muscle is chemically communicating back to the rest of the body. It's shifting the whole metabolic environment of the tissue.
Crucially, the FES-induced myokine release directly upregulates the expression of insulin-like growth factor 1, or IGF-1.
Which is a big deal.
A very big deal. In skeletal muscle, IGF-1 is one of the most potent anabolic signaling molecules we have. It forcefully commands the tissue to synthesize protein, build structural density, and just grow stronger.
So it's actively flooding the local environment with anabolic signals.
Yes.
So just to be clear, this electrical stimulation is literally acting like a molecular switch. It's turning on the build muscle genes and turning off the destroy muscle genes.
Yes, that's precisely what is happening. It's simultaneously suppressing the catabolic pathways. The electrical stimulation actively downregulates ubiquitin-ligase genes like MERF1 and atrogen-1.
Ubiquitin-ligase genes. Those are the bad guys in this scenario, right?
Yeah, they act as the biological demolition crew. In a denervated, disused muscle, MERF1 and atrogen-1 are heavily upregulated. They just relentlessly break down muscle proteins and drive that rapid atrophy we discussed.
So by downregulating these specific demolition genes while simultaneously spiking the builder, IGF-1, FES literally reverses the metabolic state of the muscle from rapid decay to aggressive rebuilding.
If we connect this to the bigger picture, that molecular switch is precisely why this intervention is non-negotiable for older stroke survivors facing sarcopenia.
Right, it's not optional.
Now, the review is careful to note that direct, long-term, large-scale proof of overall systemic muscle mass increases specifically in older stroke demographics. That still requires further longitudinal study.
Sure, science takes time.
But the documented doubling of strength gains, underpinned by these undeniable transcriptional changes, it paints a very clear picture. FES is not just a crutch, it is a profound biological intervention.
It comprehensively addresses the pathology on multiple fronts. It structurally rebuilds the hardware by manipulating gene expression at the cellular level, while that sensory feedback loop permanently rewrites the software in the motor cortex.
Exactly. And the fact that this dual-action therapy is achieved non-invasively, utilizing adjustable surface electrodes that synchronize flawlessly with the patient's intended movements, it makes it an incredibly elegant medical technology.
It really does. So what does this all mean? Well, for you, whether you are navigating a stroke recovery protocol, maybe supporting a family member through rehabilitation, or honestly just fascinated by the extreme resilience of human physiology, this Kyung Hee University review dismantles the old paradigms of neurological damage.
It really shatters them.
We used to view the severed connection between mind and body as permanent, just static. But FES proves that both the hardware and the software are remarkably plastic. By deploying precisely timed external electrical impulses as a temporary bridge, we can actually coax the body into physically repairing its own broken networks.
Right. It transcends merely preventing a foot from dragging.
Exactly. It is fundamentally about restoring agency, mobility, and independence to older adults.
It entirely redefines rehabilitation.
Right.
We're moving away from passive recovery and fully embracing active nervous system engineering. And understanding these mechanisms leaves us with a highly provocative question for the future of the field.
Yeah. Because if functional electrical stimulation is this robust at hacking the brain-muscle connection, if it can effectively reverse atrophy, downregulate demolition proteins, and forge brand new neural pathways long after a devastating neurological event.
Could we eventually utilize this technology preemptively?
Right.
As our understanding of these transcriptional mechanisms deepens, could we deploy targeted FES protocols to ward off standard age-related muscle loss and cognitive motor decline before an injury or stroke ever even occurs?
It makes you wonder. We spend all our clinical energy scrambling to repair the fiber optic cable after it gets sliced. Perhaps the future of preventative medicine lies in using targeted electricity to continuously upgrade and reinforce that cable so it never degrades in the first place.
It's a fascinating possibility.
Definitely something to mull over the next time you effortlessly reach out to grab your coffee cup, totally unaware of the millions of electrical signals firing perfectly in the background. Thanks for joining us on this deep dive.